We are discussing the problems with commutation, problems caused in commutation, and we have discussed that there are two problems associated with commutation. One is the problem of armature reaction, and second one is the LdI by dt voltage issue. So, associated with armature reaction basically causes two issues. One is the shifting of the neutral plane, as we have seen, because of the generation of armature because of the generation of flux produced by the current flowing through the armature conductors, the magnetic field, the main magnetic field produced by the field windings gets distorted, and the neutral plane basically shifts because of increase in the magnitude at the leading end of the poles and decrease in the magnitude of magnetic field at the trailing end of the poles. So the magnetic neutral plane basically gets shifted, because of which we actually tend to place the brushes along the magnetic neutral plane along which the induced EMF is zero, so that smooth commutation takes place. But since the magnetic neutral plane has shifted, EMF induced along the original plane is no longer zero, so brushes need to be shifted to the new magnetic neutral plane where EMF induced will be zero, so that smooth commutation will take place, or else it can cause sparking. It can cause basically sparking at brushes, and may in severe cases cause a flashover that may damage the DC machine itself. Second issue that's caused because of the armature reaction is the flux weakening. Uh, so what happens basically is that the flux of the machine gets weakened. The main magnetic flux that was produced by the field windings uh, is reduced. To understand this, let us take a magnetization curve. The machines basically tend to operate near the saturation region. Uh, uh, there, the flux is added by the armature. As we have seen, at this end the flux gets added, and at this end the flux gets subtracted uh, from the main flux. But the increase in flux is less as compared to the decrease in flux. What we have seen is that because of the increase in flux phi I, and if this was the average flux earlier, phi phi d will be more predominant as compared to phi I, because of the machines tend to operate at the saturation region. So increase in flux is no longer as much possible for the machine. Increase in flux is not as much possible as the decrease in flux is. So what happens is, uh, because of the operation of the machine earlier at the saturation point, the increase in flux under the where the pole magnetomotive force basically adds to the main flux, increase in flux is not as much as compared to the decrease in flux where the pole magnetomotive force is basically reduced by the armature mmf. Fine. So phi d is more as compared to phi I. So the decrease, so you can see that the average flux, the net result is that the total average flux is basically decreased. So this will so because of the decrease in flux, as we have seen, we derived the equation for induced EMF as well as for torque. We have seen both EMF as well as torque is proportional to the flux. So both in case of generator as well as in motor, the decrease in flux will have a significant impact. Uh, it will simply mean that in case of generator, the induced EMF will be decreased. Fine. That means actually the voltage that the generator will now be supplying to the output will be decreased. And as far as the motor is concerned, what will happen is that when we'll actually derive the speed equation also when the flux will be decreased, because when we'll derive the speed equation, we'll see that speed is actually inversely proportional to flux of the machine. So what happens in case of motor is that when the flux will decrease, speed will increase. Decreased flux means increase in speed. So because of the increase in speed, this actually is a cause of concern. It can basically result in uh, the increase in speed can basically cause the mechanical system to fall into a runaway condition, because we have designed the speed, we have designed the motor for mechanically it will be able to handle a somewhat amount of speed. Beyond that, if we increase the speed, the mechanical bearings it will fall down, and it can actually cause the motor to fall into a runaway condition. But also because of the increase in speed, uh, inversely what happens is the magnetomotive force produced by the field windings will also again decrease. That means it will cause further decrease in flux. That will cause further increase in speed. So this will actually lead to a runaway condition. Flux decreases, that means the speed will increase. Increase in speed basically causes the flux to decrease further. That will cause the speed to increase again. That actually leads to a runaway condition where the motor will no longer be able to operate uh, and will fall apart. So that means actually the motor will ultimately stop because the power may fail, or it may simply uh, the motor might just destroy itself because of the huge increase in speed. The bearings of the mechanical bearings will be destroyed. There are two effects of armature reaction. One effect is the shifting of the neutral plane. Fine. Because of the shifting of the neutral plane, uh, the brushes were actually placed along these directions, so that spark, because along the magnetic neutral plane EMF induced will be zero, so brushes are placed there so that smooth commutation takes place. While one brush connects between two different commutator segments, the EMF induced means zero means commutation process will be smooth and the current reversal will be smooth. But when the magnetic neutral plane shifts, EMF induced along the magnetic neutral plane is no longer zero, so the brushes will actually cause sparking, because EMF induced, because while the transition of one commutator segment to another commutator segment at the brushes, it will no longer be supported by zero induced EMF. There will be some induced EMF along this plane. So we need to shift the brushes along the new magnetic neutral plane. That's only possible if we know the intensity of the load. Fine, because if the load keeps on changing, the armature current will change. So accordingly, the magnetic neutral plane will change further or less, depending upon the amount of amount of armature current. Second is the case of flux weakening. The machines basically tend to operate near the saturation region. So the armature flux aiding the field flux will be less because increase in flux will not be as much because it's already near the saturation. So increase in flux will not be as much as compared to the decrease in flux. The decrease in flux will be much more. What will happen is that uh, system, the average flux will decrease. That means the flux is reduced. Because of reduction in flux, the generator will induce lesser EMF. That means will supply lesser terminal voltage will be supplied from the generator. In case of motor, decrease in flux basically means increase in speed. We will derive this equation of speed with respect to flux. That will actually cause the motor to go into a runaway condition. The second issue that we need to discuss with regards to commutation is L di by dt uh, voltage issue, or what's also known as inductive kick. So normally, if this is our arrangement of commutator segments, this is 1, 2, 3, 4, 5, and so on. Fine. So the commutator is rotating. We are actually laying this flat. It's rotating along with the armature of the DC motor. So say for example, the commutator is moving in this direction. Now at each commutator segment there are coils attached, and let us assume for the time being it's a lap winding. Fine. So brushes are placed at those locations where reversal of current basically takes place. So in this coils the current will be flowing in this direction, while as in these coils the current will be flowing in these directions. Uh, so the commutator is rotating when at this time the brushes are located at 3. After some time you'll see the brush segment will be here 3, commutator segment will be here 3, commutator segment 4, and the brush will be here, and finally the brush segment 4, 5, 3, the brush will be located entirely along the commutator segment 4. Fine. So this is what actually basically is happening. The commutator is rotating, the brush is stationary, the brush is placed at one point only, uh, and the terminals of the DC motor from where we actually it's a motor, we actually feed the voltage from here, or if it's a generator we actually receive the voltage from here. So the brush segment basically will move along the commutator. At some point of time the brush will be in contact with both 3 and 4, and then it will be again in contact with 4 only. So what happens in an ideal commutation is that this motion and the reversal of current through these brushes takes place in this fashion. Fine. So say for example this current is 20 amperes. That means this current will be 10 amperes. This will be 10 amperes. So initially 10 amperes of current was flowing, and the brush reaches the beginning of segment 3, or you can say the brush reaches the beginning of segment 4 at this point. Fine. After that uh, from 3 to 4 the current has to shift, so there will be a current will decrease, and and eventually what will happen, brush clears end of segment 3, this will be the case. So ideally speaking, the current reversal should take place in this fashion. This is the point when brush reaches segment 4. Fine. The brush is placed here at segment 3. This commutator is moving in this direction. Fine. So brush will, the commutator segment 4 will come in contact with the brush. So at the beginning of that, now the reversal of current will now take place from 3 to 4. Initially, all the current was being uh, transferred to the brush through commutator segment 3. Now the current will be transferred to the brush through commutator segment 3 as well as 4. So ideally, this is a linear relationship, and the current should fall uh, in brush segment 3, and at the end of and should uh, eventually be equal to, this will be at the midpoint of 3 and 4, when the brush will be placed half at 3, half at 4. Eventually, when it will be clearing, this will be brush segment clearing segment commutator segment 3. Fine. So all the reversal of current now has taken place. So finally, this is minus 10 amperes. So current has flown from commutator segment 3 to commutator segment 4 through the brush, and ideally this is what should be the graph of this flow. So what will be the ideal clearing time? What should be this? This is actually time versus current graph. So what should be this time here? If I write this equal to capital T, so what should be this capital T equal to for ideal commutation? So assume that the rotor is the speed of rotor, or the speed of commutator here approximately is 1000 RPMs, and there are 50 commutator segments. So time taken for the system to reach back will be equal to 1 divided by 1000 into 50. And if we are converting this into seconds, then 60 divided by 1000 into 50. So that is approximately 0.0012 seconds. So ideally this commutation time should be equal to, this commutation time will be equal to 0.0012 seconds for this system. Now with this in mind, that means the rate of change of current, how quickly the current has to change, rate of change of current will be equal to, will be given by di by dt. Fine. So if we are assuming here, we have assumed here there is, it is 20 amperes of current is flowing through this. 20 divided by 0.0012 equal to, that gives us 16666.67 ampere per second. So this is the rate of change of current, how quickly the current is changing from once the brushes short the commutator segment. Fine. So ideally, this is a linear graph, and this should be taking place, but the but we understand that there will be even there will be a slight inductance in this system. Therefore, because of that slight inductance in the loop, inductive voltage will be produced, and that voltage will be equal to L di by dt. So even if L is equal to 10 millihenries, because di by dt is significantly very large, that is 1666.67 amperes per second, this voltage will be significant enough and will actually cause the sparking of the brushes. This voltage will be very high, and that voltage will cause sparking in the brushes. So this commutation problem is induced because of the inductance in the loop that is naturally present in the system, and because of the rate of change of current is already very high. Even a small inductance in the loop, even if it is 1 microhenry, a significant amount of 1 millihenry, a significant amount of voltage will be induced, and that voltage will actually cause the brushes sparking at the brushes, may cause arcing problems, and may actually cause the failure of the brush and commutator segment. So this problem is actually induced also because of the shifting of the magnetic neutral plane. Fine. We have also discussed this there also, because there also voltage will be induced if once the magnetic neutral plane will be shifted, voltage will then also be introduced along the brush segment. So the cause of the production of voltage will actually cause the sparking at the brushes. What will happen is that the current will no longer, the reversal of current will no longer be linear. It will be something like this. Right? So this is your so here in this graph, this represents your actual commutation. This process is known as the commutation. The reversal of current from one commutator segment to another through the brushes is known as commutation segment. Is known as actual commutation. When taken into account with the inductance, when taken inductance into account, the actual commutation will be like this. The current will no longer be completely reversed by this amount of time. Right? So there will be some voltage that will still be left over. This will actually cause the sparking at the trailing end of the brushes. And this here represents your ideal commutation. What should have been, but because of the inductance introduced in the loop, because of the windings and the brushes itself, the commutator segment, all these will result in some amount of inductance being introduced into the system. That inductance will actually result in the production of inductive voltage kick, that's LdI by dt. And since di by dt is already very large, LdI by dt will be significant amount to actually cause the brush to fault. Fine. So these were the issues that we see in commutation. Now, how to mitigate these issues, how to solve these issues, how to address these issues. Solutions to the problems with commutation. Fine. So there are three things that we can do. One is brush shifting. Second is use of commutating poles. or what are also known as interpoles. And thirdly is the use of compensating winding. So first one, brush shifting. As discussed previously also, when the magnetic neutral plane will be shifted, we need to make sure that our brushes are placed in the new magnetic neutral plane. So how do we do this? So this is the earliest of the ideas that was actually put forth for addressing both addressing shifting of magnetic neutral plane as well as issue with LDI by dt effect. Fine. So both these two effects, that's the LDI by dt voltage kick as well as the shifting of the magnetic neutral plane, can be uh, improved by shifting the brushes. Fine. So once we shift the brushes in the new magnetic neutral plane, we'll be able to reduce the voltage. And but there is a serious drawback with this, as we do not know by what amount the magnetic neutral plane will shift. This shift is basically dependent upon the load. So every time the load increases, armature current increases, the flux produced will be more, armature flux will be more. So the shift will be more. If the load is reduced, the armature current will be less. The magnetic field produced by the armature will be less. So the shift will be lesser. So we do not know exactly where to place the brushes. So this was more of an manual approach to shift the brushes. So once we place the brush in the new magnetic neutral plane, the brushes will be placed at the location of zero induced EMF. Therefore, the problem of sparking will be reduced. Uh, However, there is another issue that's caused by the shifting of brushes, and that issue is the reduction in the, it basically aggravates the flux weakening of the system. So uh, this we can show basically using the vector diagram. So earlier the field pole, this is your magnetic field, magnetomotive force produced by the field windings or the poles. This is the magnetomotive force produced by the rotor. So this is your net magnetomotive force as a result of these two vectors. What happens with the shifting of brushes? This is when brushes are at original magnetic neutral plane. The original magnetic neutral plane is also known as the geometric neutral plane. So you can basically also refer to as the GNP, the geometric neutral plane. And it will be always perpendicular. So it will not, the geometric neutral plane will always be there. What happens is with the shifting of brushes, Fr will be in the rotor magnetomotive force will basically be no longer perpendicular to the field, the magnetomotive force produced by the field. Therefore, the new net will be F net 2. So if you can clearly see that F net 1 is basically less than F net 2. Fine. So if if we take this as an armature, and these are your field poles. The FP, the magnetomotive force, FP will be in this direction. Fine, this is the net magnetomotive force that will be produced by the field windings. And initially, the brushes are in this direction, the magnetomotive force is in this direction. FR, that's basically the magnetomotive force produced by the armature windings, will be perpendicular. Now, with shifted magnets, with shifted brushes, brushes being placed at the old, at the new magnetic neutral plane, FR will be in this direction, while as FP is still in this direction only. So there is basically an angle produced between FR and FP that will cause the flux weakening in the system. So what we can do is, so brush shifting method basically helps us reduce the sparking, helps in reduces sparking of the brushes, but because of two issues. One, we do not know exactly what will be the load, so we cannot exactly predict where the magnetic neutral plane will be, so it is more of a manual approach. Two, it causes the flux weakening. This method is more or less obsolete and is not used nowadays, except in very few smaller DC machines. In such cases, what we do is uh, keep we basically predict the magnetic neutral plane at 2/3 of the load and accordingly place the brushes. Fine. It is an obsolete method, is no longer used nowadays except in smaller DC machines where magnetic neutral plane is predicted for 2/3 of the load. Not DC machines, motors only. Fine, this is not even used in DC generators anymore. So we predict the magnetic neutral plane for 2/3 of the load. So if the load is less than that or more than that, the magnetic neutral plane will be around the predicted magnetic neutral plane. So sparking will be lesser as compared to if it were in its original position. So this is the first method, that is using brush using by shifting the brushes. The second is using commutating poles or interpoles, and third we have the compensating windings. Those two methods we will take up in the next session.